Hello? We can't. The bus is too late. Hi, thank you for coming. We were going to wait till a bus arrived with students and professors, but the bus is delayed in traffic. Apparently Constitution Avenue is completely blocked. I'd like to welcome you to the inaugural symposium of the Yvonne C. Brill Lecture Series. And now I would like to introduce Dr. Dan Moat, President of the National Academy of Engineering. Dan?
Well, thank you, Elaine, very much for this introduction and for this opportunity. I mean, this is a very special opportunity. I feel honored to have this opportunity to come and welcome you to this Yvonne C. Brill lectureship of the aerospace engineering. This is such a great idea. I remember about a year ago when Elaine came to me and talked about doing this for Yvonne Brill and how important it was to do it, and I agreed completely. And of course, she then recruited all of you and others in AIAA to put it all together, which is really a wonderful outcome. I have to admit, I didn't know a lot about Yvonne Brill for whatever reason until we started to have this conversation. But I've become extremely impressed with her. In fact, the more I've thought about her since, the more impressed I've gotten every time I think about her history and how she lived her life. Of course, this first lecturer, Adam Stelzner, it turns out that we actually are almost related. We lived a couple hundred yards apart in Sausalito. We went to the same grammar school, we went to the same high school. More or less a generation apart, but hey, what's that, more. But had not quite all the same teachers, but some similar experiences, though I don't play the bass. And he is certainly a spectacularly credible person to give this Yvonne Brill lecture. He fulfills many of the things that describe her. Of course, she is an AIAA honorary fellow and an NAE member. And I just, my big regret is not knowing her. But she was elected to the Academy in 1987 for spacecraft propulsion, basically her electrothermal hydrazine thruster, which she invented in 1967. And was patented in 1972 and flown in 1983. And this invention, I understand, I'm not expert at all in this, but I understand that it is still the industry standard for geostationary satellites in terms of it. When she was elected to the National Academy of Engineering, only 1%, that's 1.0 more or less, 1% of the members were females. So she was a pioneer there too. Of course, she had no degree in engineering at all, but that's not a big surprise, and over 25% of the members of the National Academy of Engineering have no degrees in engineering. Some have no degrees at all, as a matter of fact. You don't get elected to the Academy by what you call yourself or by what degrees you have. You get elected by what you have done, and she certainly did a lot of great engineering. Her history in University of Manitoba and how she didn't get into engineering, even though she wanted to get in, is quite funny and humorous these days. But it didn't seem to slow her down at all. I mean, she had this tremendous capacity to keep moving. That was very apparent throughout her life. Now, at the Academy, she served on many committees, at least 20 committees. In the Aerospace Engineering Peer Committee, she was there on a normal term, but she was also served as vice chair and chair of that committee. She served on the Space Studies Board at least twice for many years. She was on the Strategic Earth to Orbit Propulsion Systems Board. She was on a review of NASA's Astrobiology Institute. She was on the Reusable Launch Vehicle Technology and Test Committee, and she was on NASA's Earth and Space Science Missions Committee. She won the National Medal of Technology and Innovation in 2011, and she was elected also to the Inventors Hall of Fame in 2010. So she always went her own way. I mean, what I deduced from reading about her, she's a person who always went her own way. She was kind of always independent, but caring in mind and spirit at the same time, and she just did what she believed was right. Clear thinker, a pioneer, not a follower. Really didn't mind being a team of one. Even seemed to enjoy it in a way. But she had this remarkable ingenuity and this capacity to bring her visions to life. You could see that right in her record. She didn't do things for herself either. She did things for other people and had wisdom for other people. And that's just the way she wanted to live her life. It's so reassuring to know people like Yvonne. Now, I really applaud the AIAA, Annie Lane and her committee, colleagues, and many of you here, if not all of you here, for recognizing this remarkable and remarkably accomplished engineer with this lecture, really to keep alive the spirit of Yvonne's visionary, independent, and ingenious thinking on how women and men might think about their integrated personal and professional lives rather than conflicted professional and personal lives. And that really jumps out of her history very remarkably and is extraordinarily unusual. So welcome here today, and it's a great pleasure to be here and to make these opening remarks in this very important lecture. Thank you very much.
President Moat, Dan, thank you very much for kicking off this really important afternoon. I'm Richard Truly, and I'd like to just spend a couple of minutes telling you a little bit about what you're going to hear today. Today is a very special treat. This is the first ever, but it's only the first, Yvonne Brill lectureship in aerospace engineering. It's important, and I am so glad that I can be here and participate in it, and I can tell you that Yvonne would be delighted that you're here as well. First, an apology. I have to be in Denver first thing in the morning, and the airplane leaves at 4, so I'm going to be ducking out pretty quickly, but I have Yvonne's permission. The driving force behind today is Yvonne herself. Because of her work and her the things that she did for other people, she gathered around herself friends and colleagues and family that were so loyal, and we didn't really quite realize that until after she was gone in some ways. But I have to say that there was a deputy driving force, and that's Elaine. And I'd like to give Elaine a round of applause, because we wouldn't be here today without her. But these friends and colleagues had the idea that we wanted to do something in Yvonne's memory that would live on in the profession that she really devoted her life to, and the people that were in it. So we decided maybe, it's hard to raise support and particularly money, but maybe we could raise some money to endow a lectureship that would live on. And the most amazing thing happened. We never had to have a campaign. Somebody said, "I'll give." And another person said, "Check's in the mail." One person gave $10,000, and we raised enough money to endow a lectureship. And then we needed organizations to step up. And again, Elaine and her record was the driving force. And so the National Academy of Engineering the AIAA, and the University of Maryland stepped up as organizations to join her friends and colleagues to make today happen. You're in for a treat. Let me describe very briefly what today is going to be about, and I won't steal Adam's thunder, but before the break you're going to hear from three individuals. First, Steve Batel, the president of Batel Engineering, a great engineer and a great friend. And Steve is going to mention some things about Yvonne's professional life, her technical capabilities, and her accomplishments. Then Jill Tejan, who is going to talk a little bit about what Yvonne meant to other people. And Jill is president and CEO of Technically Speaking Incorporated and the past president of the Society of Women Engineers. And then finally, Matthew Brill, Yvonne's son, is going to talk a little bit about what Yvonne's family and tell us a little bit of a more personal input. So in other words, you're going to hear about Yvonne Brill, the rocket scientist, Yvonne Brill, the mentor, and Yvonne Brill, the mom and grandmom. And then we're going to have a break, and at that point you will get to hear the inaugural Yvonne C. Brill Lectureship in Aerospace Engineering, and it's going to be a great afternoon. Thank you very much, and Steve, it's up to you.
Thank you, Dick, and I think we'll let everybody get seated here since we have our student bus evidently has arrived. So my name is Steve Batel. I met Yvonne, actually. I knew of Yvonne, but never had had the opportunity to get to know her until we both served on the Space Studies Board. She noticed that I had Batel Engineering on my name card, and so she came over and decided to sit with me, and the first thing she said is, you know, engineers always have to sit together. And so it certainly endeared me to her, and I had a unique opportunity over the next several years to spend quite a bit of time with Yvonne, including visiting her at her house in Princeton, my son, and I came to admire her very much, and she really became one of my mentors, a personal mentor. I'm not going to speak about that part because I think Jill is going to be spending time there. But what Elaine asked me to do was to spend 12 minutes covering Yvonne's 60-year technical career. So in engineering speak, we won't use logarithms, but it's a 2 million to 1 compression ratio. And as was mentioned by Dr. Moat, she was very energetic, so there was a lot of stuff. When I went through her career, I was even astonished and I know she had been very active, but my goodness, there was so much stuff and so many pictures and so much information. It was a wonderful thing. So the title of my talk is Yvonne Brill, Technically Speaking, and it's a retrospective from my perspective, but I think it also will resonate with all of you. Here, Yvonne, when she was younger, this is actually her, as best as I can tell from looking at the documentation, this is actually the dual hydrogen tanks on the Tyros N spacecraft, or one of the Tyros series, and that's in that grouping in the mid-70s. And she had her hand on a lot of hardware, and I think one of the things that I think was unique about Yvonne is that she both spent time as a system engineer thinking through the top-level engineering problems associated with spaceflight, but she also spent, as you will see, a tremendous amount of time with her hands on the actual hardware, as well as, in many cases, her hands on individual engineers and people as a mentor. So I first just started with a quick series of pictures. A number of these are going to be shown again, so I'm only going to go quickly, but there's clearly a tremendous amount of prestige associated with the things that she's done. This is the, I'm afraid I have to look over here. This is the National Medal of Technology here. This is the Inventors Hall of Fame induction. There's many cases you can see with the Society of Women Engineers and other engineering organizations involving women that Jill, I'm sure, will be speaking about, but it was very important to her, and as a result, I felt it was important in a retrospective to at least recognize the impact she's had on not only myself, but on women as well in their career paths. This picture here is actually one of her favorites. I extracted this actually from one of her talks, and it was actually a cartoon that was drawn by one of the other engineers at RCA. She was the only, as it turns out, and she was very proud of this, she was the only propulsion engineer at RCA, whereas Hughes, she kept pointing out, had 75. And so she was the one and only, and she always said it was because it was quality, not quantity, that was important. And so her colleagues drew this, and as one of their popular pictures that they had with her holding the match, lighting the rocket, and if it's sort of cut off, but at the top, one of the engineers is holding on to the nose cone. So it was quite a lovely thing, and you can get more information on this if you want to look up the MIT lecture that she gave in 2009. Now the key pictures here, there are three that I'm going to talk about more. One is this picture here associated with a Teflon pulse plasma thruster. This is her invention of the hydrazine thermal thruster, and this is actually a picture of them testing this on what they call the Frisbee court. The Marquardt engineers, they were demonstrating this for engineers and for the senior management at RCA, and they actually, the Marquardt engineers flew down the thrusters with a fully loaded hydrazine tank on the airplane. She was very proud of that and the fact that it actually worked once they fired it here. You can't see it, but she has like a little push button wire that goes over, and she was actually activating the thruster on the grass outside of their facility there. So when you talk about the legacy of Yvonne, the first word that comes to mind is creative. I mean, she had a lot of energy, but she also had a lot of ideas. Her training in chemistry and mathematics served her well, first as a system engineer. She was at Douglas and then the RAND Corporation. She was at Wright Aero, FMC, NASA, and Inmarsat, as well as RCA. And the thing that, so whereas she really worked as a propulsion engineer, it was her system engineering training that really created the opportunities that she sought in her career. And as you'll see, they really came about in trying to figure out how to best serve satellites in the propulsion field. Some of the satellites she was involved in, she was involved in the Tyros series. Atmospheric Explorer is actually a hidden jewel. That was an RCA spacecraft that did deep dipping into the atmosphere, and it required really what was the first application of special propulsion tanks in order to keep the fluid distribution stable, because you didn't want to have the spacecraft dip too deeply. If you lost the center of pressure, the spacecraft would tumble into the atmosphere rather than skip back out again. So it was actually a very innovative thing that she didn't talk very much about, but it actually is used on a number of spacecraft now and has become another industry standard. I picked only the ones that really had a lot of innovation associated with them. The Nova spacecraft was really quite a tremendous series of spacecraft through the 60s and 70s into the early 80s. And it was a very complex spacecraft used as a pre-GPS for navigational aid. But one of the things that was very important on it is it was the first spacecraft that used pulse plasma thrusters effectively. And this was the thing you saw in the picture, and you'll see again in a moment, that where she was deeply involved in the not the invention, but the application of such thrusters. She recognized that the ISP, being on the order of 3,000, was so much greater that it really had great advantages for station keeping in low Earth orbit. So in researching her career, it was interesting to go back and really look, and this is a wonderful journal. I don't know if any of you have seen it, but when you go through the journals, it's amazing the amount of work that was being done in the 60s and 70s, at not only RCA, but at Bell Labs, of course, and other places, but the amount of engineering papers and documentation that came out in these types of technical journals. And here I've highlighted Yvonne's paper, which is impossible to read here, but I will read it for you. This is 1972, but it's the Propulsion for Geostationary Spacecraft. As you know, you had heard that she had invented what she called the resistojet thruster in the late 60s in 1967. In 1972, the patent had been applied for, and so she and some colleagues wrote a wonderful paper that discussed in detail the entire application of and use of the thruster in orbit. This is actually her patent disclosure, and I think it's quite wonderful when you see how detail-oriented Yvonne was. I mean, you don't see many patents where she tells you everything, including where the filter has to be, the valves, and the entire she just told you the whole thing. It wasn't like she was going to leave anything to chance. If you're going to use this patent, you'd better use it exactly as she specified. And it's actually, if you were to look at any current spacecraft, you would see almost any geostationary spacecraft in particular, you would see nearly the same implementation. And so this is from the early 1970s, and it's representative of things that we're flying now. So 40 years later, her visionary design is still being used in the majority of geostationary spacecraft. And this is of the famous curve where she figured out the difference in the ISP and how much it could save over the lifetime of a satellite. What is interesting here, of course, is that years in orbit were much shorter than they are now. I mean, this is in the early 70s, and it was at this time that satellites started to exhibit lifetimes on the order of 15 or 20 years or more. But of course, the space age wasn't that old in 1972. So she was visionary in many ways. So just to talk about propulsion technology for geostationary spacecraft, this is actually her paper, and it's available on the web if you want to pull it up, or I can give you a copy. But I wanted to sort of show you the different things that Yvonne was involved in. First, at the top, this is the Teflon pulse plasma thruster, and in many ways, this is the thing she was the most excited about. If you were to talk to her, she invented, the electrothermal hydrazine thruster, but that wasn't her baby. Her baby was really pulsed, plasma technologies. And as she talks about it in some of her talks, in that time frame, they had the technology for eroding or using the fuel, but they really didn't have the electronics to power it. And one of the things that I think was most important in the late 60s and early 70s is that Yvonne recognized that power was going to be available in geosynchronous orbit. In other words, you'd have enough power to be able to use alternate thruster technologies, and that the trade for power versus carrying propulsion material, in particular, you know, hydrazine, for example, that mass balance was really in favor of going electrical. And so she was really the pioneer for all of the electrical spacecraft that we see today. And her thruster, which was a hybrid, the one that's in the technician's hand, was the very first thruster of the type that was flown. And as you'll see, it remarkably looks like the ones they're flying now. Was really a pioneering thing that's still being used, because for the most part people are still carrying propulsion fluids to orbit. Now, I'm not going to go into a lot of detail, but I want to kind of just show you in 30 seconds the basis of her genius. In that when you look at over here, you see sort of the range of technology that are available for propulsion, and we're really talking about the electrical grouping, which is over on the far right. And and this is where you in fact have, and also the hot gas ones right here. And what she recognized was that if you're going to carry hydrazine, and remember this was in the early stages of hydrazine, the fact is that it had an exothermic decomposition. It was usually done with a catalyst, what's called Shell 405 catalyst. It was a alumina iridium compound that you use in what they call a catalyst bed. And by heating up the hydrazine, the gas generation was tremendous, and you get up to about 800 degrees. And you'd exhaust that out the thruster, out the nozzle, and that was what got you your thrust. And the ISP for that type of system was in the order of 220 to 225. What she realized was that that ISP was really the function of two things. It was the square root of the temperature over the molecular mass of the ejected gas. And what she realized is that if you could make the gas hotter, you'd gain thrust. And it turns out that easily within the technologies that were available, it was possible to heat the hydrazine up to 3,000 degrees from about 800 degrees. And so the gain in ISP was actually substantial, and that was a tremendous return for the same amount of fuel. You got a fair bit more ISP. In fact, it went up to about 300. And these were all calculated by Yvonne, and then were proven to be correct. So the basic idea is that you have a standard cat bed heated thruster, and then you inject the gas into a preheated, a very high temperature chamber, where then it's ejected out the nozzle. And so the reheating of the gas increased the ISP by 20%, 25%, and that was a direct fuel savings. That was the genius of Yvonne's invention, and in fact, nobody has done it better yet with regard to using liquid propulsion. So I'm not going to go over this because we're going to run out of time, but it turns out this is a current thruster design, and if you look at the previous page and you look here, they're really identical. Right now, Aerojet is the manufacturer of these, and they're using almost exactly the same thruster with almost exactly the same performance today, and on many, many spacecraft, in fact, hundreds of spacecraft. And so it's really changed the nature of the communications satellite business. And in fact, this is just to sort of give you a picture of all the satellites and the electric propulsion. You think of Yvonne's contribution to electric propulsion in its totality, not just with regard to her invention, but also with regard to the electric propulsion systems that are available. You can see that the growth has been nearly exponential, and will continue. And thus, Yvonne is remembered with our work now in the satellite business, not only for her technical accomplishments, but the legacy that she now offers all of us through satellite technologies that we're flying. Thank you very much. Now I'd like to introduce Jill Teach-In, who's going to take over, and you need to, okay.
Thank you, Steve. He had a title for his talk, which is the name of my company, so I actually really like that. And if I had a title for mine, it would be There is Only One Yvonne Brill. I had to laugh. It was 2009, and Yvonne was here in DC for a meeting, and she called me because she had heard that Yvonne Brill was receiving the John Fritz Medal from the American Association of Engineering Societies, and she was pretty sure it wasn't her. But she really didn't know of another Yvonne Brill. And so I assured her, yes, that she was getting the Fritz Medal. Yes, I had nominated her for the award without consulting her. In fact, as soon as I realized that she had gotten the Fritz Medal, I really got into significant action, nominated her for quite a number of other awards which you've heard about today, including the National Medal of Technology and Innovation. And I had the privilege of being at the White House with her family when she received that award from President Obama, as you saw, in October of 2011. There might have only been one Yvonne Brill, but she made a significant difference in the world for many people, and particularly for many women. She mentored many, nominated many, and throughout her long career was a role model extraordinaire. In fact, I would like a show of hands in this audience of the people for whom she completed successful nominations for, and I know that some of you have to raise both hands. See? Her efforts helped boost self-confidence in all of her nominees. She was demonstrating the ultimate in encouragement and kind words. I considered Yvonne my soulmate. We both understood the criticality of nominating women for awards. Of course, she was also a wonderful woman, friendly, and with a family. I've known her daughter, Naomi, for over 20 years and have now had the privilege of meeting her sons, their spouses, and her grandchildren. And I had the privilege of meeting her husband, Bill Brill, when she was inducted into the New Jersey Inventors Hall of Fame. And I want to share a little story with you. In 2007, I was invited to speak at the Society of Women Engineers, and I'm wearing my SWE pins today. That's what we call it, SWE, at the regional conference held at the New Jersey Institute of Technology. And I invited my aunt, who lived in Parsippany, New Jersey, to come because my uncle, her late husband, had attended the Newark College of Engineering. Yvonne had told me she would be there and that she wanted to consult on a nomination with me, and Lorraine, that was your nomination. My aunt and I arrived at the venue. Yvonne and I consulted while my aunt busied herself reading the New York Times. And when Yvonne and I were done, I introduced her to my aunt. I had to go handle the AV, and then it was time for dinner. There was a seat next to me at the head table for my aunt. I found her. She said, "Nope, I'm not sitting with you. I'm sitting with Yvonne." According to Naomi Brill, Yvonne's daughter, Yvonne became passionate about nominating and advancing other women after she received SWE's Achievement Award in 1986. Truly, she was on a mission. She worked tirelessly from 1986 until her death in 2013 to bring recognition to women through SWE awards, fellow grade nomination or membership in SWE and AIAA, election to the National Academy of Engineering. In fact, she and I were working on a nomination together the week she died. She was also an incredible mentor, and I would like to read part of a nomination letter of recommendation for her Society of Women Engineers Distinguished Service Award from Florence Hudson, an IBM executive. Yvonne has been my mentor since I was an undergraduate engineer at Princeton University, where she was our SWE collegiate advisor in 1977. She nominated me to my internship at the NASA Jet Propulsion Laboratory, where I worked on future missions around Jupiter. My lifelong mentor, she has guided me through my career at Grumman, NASA, HP, and IBM, leading to my executive credentials as vice president and director at IBM. Yvonne nominated me for the SWE Upward Mobility Award, and I was extremely honored to have her seated beside me at the 2008 SWE Achievement Awards banquet when I received the award. After all, she was with me my entire aerospace engineering career. I lovingly call Yvonne my SWE godmother. Lorraine Huckler. Lorraine, would you raise your hand, please? President of Martech Systems, received SWE's Distinguished New Engineer Award and SWE's Entrepreneur Award, both nominations prepared by Yvonne. Here's what Lorraine told me. My relationship with Yvonne was a transformational relationship in my career. I didn't even know that I was being mentored, but one day it finally dawned on me. What an amazing relationship. All the things that she did for me. In the early 1980s, 4 of the SWE New Jersey members, including Yvonne and me, used to have what we called power lunches to share successes and challenges. We talked about ideas, issues. It was refreshing. Over the years, the 4 of us drifted geographically apart, but Yvonne and I stayed in New Jersey and continued our relationship. Yvonne was completely present when we met. She listened when I talked. She never offered advice unless I asked. She asked questions, both to clarify her understanding of my statements, but also questions that helped me clarify in my own mind the problem that I was describing. She never told me that she believed in me and my ability to achieve my goals, but she showed me in numerous ways. Whenever I sought her counsel for a difficult issue, I always came away with a renewed sense of optimism. Mentor, role model extraordinaire. These words describe Yvonne. From Carolyn Phillips, another SWE past national president. I've known Yvonne since my days in New York many years ago, and she has always been active and concerned with encouraging women to enter engineering as a career and mentoring them to stay in as they progressed and realized frustrations when not progressing as they would have liked. She was always there as a supporter, lending a hand through many, many SWE activities, local and national. These activities were often led by Yvonne, but she often played a key role behind the scenes, giving others the credit. She never sought the limelight, just wanted to get the project done for women and for SWE. At over 80, she keeps going like the Energizer Bunny, still sought as a consultant and still encouraging involvement of women and supporting the women she comes into contact with. What a great role model for SWE members of all ages. And from Shirley Mccarty. Shirley, you want to raise your hand, please? General Manager from the Aerospace Corporation. I didn't know Shirley was going to be here. Miss Brill's track record for encouraging young people to pursue mathematics and science was already legendary when I met her in 1977, and she hasn't skipped a beat since. This work is even more important today than it was when she first started mentoring young students. She has fostered the Princeton Society of Women Engineers student section since its founding. She has influenced thousands of students to achieve and succeed in their academic pursuits. At conferences, she seeks out young women to share ideas with them and to gain their perspectives. If students need encouragement to jump the next hurdle or to stay in engineering, she is always there to help them realize that they can do it. When her students complete their work, she remains a mentor throughout their careers. She shares her wisdom and her incredible energy with professionals and students alike. Her fierce commitment to SWE and the SWE mission is remarkable. She can always be counted on to roll up her sleeves and get important projects done. Yes, Yvonne could always be counted on to do projects that others initiated or to initiate her own project. I believe she truly understood the words of anthropologist Margaret Mead. Never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it is the only thing that ever has. The world is better for Yvonne having been in it. Thank you. Matt.
Good afternoon. I'm Yvonne Brill's son, Matthew Brill, but please call me Matt, because when my mother called me Matthew, I knew I was in trouble for one thing or another. I would like to offer a few brief remarks on behalf of the Brill family, then I'd like to share a few thoughts on what it was like to have a mom who was a rocket scientist. I'm speaking on behalf of the immediate Brill family, which consists of my older sister Naomi, who is a retired mechanical engineer, but also very active in the Society of Women Engineers. Also, my younger brother Joe, who knew he was in trouble when my mom called him Joseph. Joe is a former electrical engineer. I say former electrical engineer because Joe's first job out of college was part of the team that built and launched the Mars Observer spacecraft in 1992. After NASA lost contact with the Mars Observer in '93, just before it was to achieve orbital insertion around Mars, Joe decided going back to school, getting an MBA, and becoming a VP at a big bank was a better career option for him. My mom was actually not entirely disappointed that Joe left engineering to go into the business world. At least she knew she wouldn't have to financially support him any longer. Well, enough of my not-so-subtle commentary that engineers should be paid more, and I promise my brother I'll never ever mention the Mars Observer in public again. Besides, I understand that in just a few minutes, we are going to hear about a much more infinitely successful mission to Mars. My brother Joe lives in Denver, and my sister Naomi lives in Minnesota. They were unable to join us here today due to other commitments. I'd also like to acknowledge some of the extended Brill family in the audience, two of Yvonne's nieces, Ellen and Marcy, and one of Yvonne's daughter-in-law, my wonderful wife, Teresa. So, on behalf of the Brill family, both immediate and extended, we would like to thank and recognize the lectureship sponsor, the American Association of Aeronautics and Astronautics, and the support of the National Academy of Engineers and the University of Maryland A. James Clark School of Engineering for making this wonderful event to honor my mother's memory possible. My mother passed away in March of 2013, and people associated with the three organizations I just mentioned, under Elaine's leadership, have been working tirelessly since that time to make this lectureship a reality. In addition, there are many individual donors who gave generously to fund this lectureship, and we also wish to thank them as well. Beyond the institutions and individuals who made this event possible, the Brills would also like to thank each one of you in the audience for attending today. If you were a friend or former colleague of my mom, you already know her professional accomplishments and the type of person she was. If you did not know my mom personally, and I see a lot of very intelligent but young-looking students in the audience today, I will share a few thoughts on the kind of mother and person my favorite rocket scientist was. She would be extremely pleased by all you students here being here today because a major focus of her life was mentorship, helping young people get into and then succeed in technical careers. She was the type of person who was always willing to share what she knew and collaborate with others to help them succeed. For example, if she had not helped me do my homework in high school, and then sometimes even in college for that matter, there's no way I could have ever become a principal-level hydrogeologist at the world's largest engineering firm. Of course, most every kid thinks their mom is wonderful. Why should I be any different? I'm not really sure where she found the time to do all the things she did in her career and all the things she did for our family. Goodness knows, my dad and us kids were not much help around the house. We narrowly missed being selected to do an episode of that TV program, Hoarders. Now, by this point in my remarks, you may be wondering what kind of man marries a rocket scientist. Yvonne's husband, my dad, Dr. William Franklin Brill, had a PhD in theoretical organic chemistry. His last job was as a visiting scientist in Princeton University's chemistry department. Those of you who knew my mom and dad knew that Bill and Yvonne Brill were a package deal, a team that was married for 59 years. They were very proud and very supportive of each other's professional accomplishments. One of my favorite anecdotes about my parents is the time my mom was inducted into the National Inventors Hall of Fame in early 2010. The evening before the induction ceremony, she and my dad sat at the banquet table with David Kapos, who was director of the U.S. Patent Office at that time. My dad leaned over and said to Mr. Kapos, quote, "You know, I have over 17 U.S. patents, and my wife here only has one. So when do I get to be in the Hall of Fame?" Unquote. Today, September 30th, is the 4th year anniversary of my dad's passing away. I don't know if there was a conscious effort to schedule this event on this day, but I will thank those responsible anyway. The way my mother dealt with the loss of a spouse of 59 years told me a lot about what type of person she was. She mourned, but she continued on with her work for the NAE committee she was involved with. She continued on helping the Society of Women Engineers with their programs and meetings, and she continued on with helping get professional recognition for other engineers, particularly women. She lived very much in the present, and once she overcame a problem, tended not to dwell on it. She always looked forward to the future, both professionally and personally. We kids did not realize our mom was a little different than other moms of that era. And by that era, I mean late 60s and the 70s, until the FBI came around the neighborhood asking questions about our mom so she could get her top secret security clearance to work on the propulsion system for the Navy's Nova satellite. By the time high school and math science challenged us kids, we knew Mom was special. She helped us do the homework, as I've already mentioned, but she also told us the same thing as what she told so many young women, high school students, as she traveled the country as part of a SWE outreach program. She said, if you don't take math and science in high school, you'll have a very difficult time pursuing an engineering or science degree in college. Remember, in that era, young women were told to take home economics or typing class instead of taking math and science in their junior and senior years. I know things are much more progressive now in high school, as my own daughter, Yvonne's granddaughter, Lauren Brill, was encouraged in her pursuit of math and science in high school. Lauren is now a freshman at Tufts University in the College of Engineering. She will be the 3rd generation of women engineer in the Brill family, which leads me to what I believe would be my mom's wish for how she would like us to remember her. Part of her legacy is that she helped others, particularly women, pursue and embrace careers in engineering, to help more established engineers get the professional recognition that she felt they had earned, to inspire young engineers to continue with their careers in engineering, regardless of the roadblocks such as discrimination and bad management. She hoped that her success as a woman pioneer in aerospace would make future career paths for women engineers easier, in that those future women would only be judged on the quality of the work and the excellence of their technical contributions. Again, on behalf of the Brill family, I thank you all for attending, and also our heartfelt appreciation to our hosts, sponsors, and supporters of the Yvonne C. Brill Lecture Series.
Thank you. We'll take a break now for about 20 minutes and then come back to hear Adam Stelzner. Thank you. Everyone, I just wanted to make a pre-announcement that there will be a reception after this, and this reception should have real food. Okay. I'd like to introduce John Anderson, who is representing AIAA, the American Institute of Aeronautics and Astronautics.
As Elaine said, I'm representing the AIAA. The AIAA, as most of you know here, is an advocate for the profession of aerospace engineering. Yvonne Brill was an advocate for our profession. And more than that, an advocate, as Dr. Moat so elegantly put it, and other people who've been on the program, that she was an advocate for young people going into science and engineering and mathematics. So I'm pleased to stand up here and say, boy, the AIAA is part of this overall honoring of Yvonne Brill. And although, I'm not going to repeat all the honors that she's received and so forth, but something hasn't been said. She joined the American Rocket Society in 1955. How many people remember? I mean, many of you were not born that. And of course, later on, about 1960-61, the American Rocket Society joined with the Institute of Aeronautical Sciences and became the AIAA. So she was a long-time member of the AIAA. In 2007, the AIAA elevated her to honorary fellow membership. She was the first woman to be made an honorary fellow. And if you look at the list of honorary fellows of the AIAA, it goes all the way back to people like Theodore von Karman, beginning in the 1930s. So that's quite an honor to be the. And she broke, so to speak, she broke the ice. We have another woman in the audience, Elaine Arndt, who is an honorary fellow of the AIAA. I didn't ask you whether you were the second one, Elaine. You can elaborate on that. But this is why I'm standing up here, to say something about the AIAA and our relationship with Yvonne Brill. The one last comment, and then I'll quit on this. Frequently, and I heard her say this several times, that in many occasions in her professional interactions, she was the only woman in the room. And I can equate with that, when I graduated in 1959 with a degree in aeronautical engineering at the University of Florida. There were 50 people in my graduating class in aeronautical engineering. 49 of them were men, young men. One was a young woman. So that kind of, you can look out today and I see a number of young women who are in my profession of aerospace engineering. And it's such a dramatic change and such a very nice change to see. And we are celebrating Yvonne Brill as one of the motivators for that kind of change taking place. So, with that being said, I'm also in the capacity of introducing the person who's going to introduce the real symposium speaker. This is Natalie Crawford. And I'm going to, just to make sure, she's done so many things, I have to read this to make sure I have it all. She's currently a senior fellow of the RAND Corporation. RAND, that means capital R, capital A, capital N, capital D. That's an acronym for one of the long-standing, prestigious think tanks in our country. Senior mentor, she's on the Air Force Scientific Advisory Board, member of the National Academy of Engineering. She's worked at RAND for 40 years or more, during which she served for 9 years as Vice President and Director of the RAND Project Air Force. She has deep substantive technical and operational knowledge and experience in areas such as conventional weapons, attack and surveillance avionics, fighter and bomber. This is good, go on and on. Aircraft performance, aircraft survivability, electronic combat, theater missile defense, force modernization, space systems and capabilities, and non-kinetic operations. And I could just go on. Natalie Crawford is a good example of the kind of person who Elaine Orrin recruited to just introduce a speaker. And so I'm not going to go any further than to ask Natalie to introduce our speaker.
So you've all heard all this technical stuff. Let me tell you one of the most remarkable things that Yvonne Brill did in her career. She took a time out to raise a family. Nobody said that today, not even her son. No kidding, she paused in her career to raise a family. I think that's fabulous. That's a great contribution as a woman, whether she's a rocket scientist or not. Her career's stellar, rockety, spacey, it's everything. It's wonderful. She welcomed me when I came to the NAE Section 1, and she was always there to give a little advice, which I welcomed every time because she was the repository for it. So I'm honored to be here. I'm honored to be part of the committee to honor her and to perpetuate this event. I was also interested to hear that Joseph, or Joe as he's otherwise known, Brill, is connected to the Mars exploration business. So our speaker, this was all a surprise to us, so the speaker is going to make a comment about that. Not whether it's good or bad, but to put it in perspective with what he's going to talk about. You all saw the Mars Curiosity land. You saw it on TV. You saw the hysteria, the exuberance, the everything. The 15 minutes of sheer terror, or whatever it was called, as the thing kind of went down like that. I was fortunate to be on the JPL Advisory Council for several years, about a decade. And during that time, Curiosity was under development, this school bus kind of thing that they're going to land on Mars. And I remember there were two challenges they had at the time. One was the radar, which I called an altimeter, so they'd know how high they were off the ground. And the second one was actuators. And I couldn't understand that. How could that be? We've built radar altimeters forever. We built actuators forever. But the problem was we need actuators to lower this to respond to this in the environment and this really, really, really heavy object that has to behave correctly and survive. I always said when I went to JPL, and I say it to Charles Alachi today, it was always and remains like going to Disneyland for me. I have got no concept of how to do those things, but it sure does make me excited when I hear about it. So we're so fortunate to have Adam here. You may stand up now and walk over here, if you will. I'm not going to go on and on. You can Google him and see the awards that he's won. He really has, I mean, this is a remarkable accomplishment, what the team did. A truly team effort led by a great leader. So without any more of that, Adam, thank you for saying yes. Thank you for being our our inaugural speaker, and we're excited about hearing what you have to say.
Well, thank you.
Thank you.
So my first reaction, naturally, after being here for the last few hours and hearing about Yvonne and everyone who's introduced, I'm immediately overcome by being absolutely not worthy of this fantastic honor. But it is true that I too, like everyone who has spoken, am energized and excited by the act, the collaborative team act of engineering, as it certainly sounds that Yvonne was. So we'll talk a little bit about engineering to Mars. You know, I have an early memory of being at the lab, and we had lost the Mars observer spacecraft, and we'd lost it in the morning. And that afternoon, I went to lunch off lab, and I came back from lab, and people were picketing. And they were picketing with signs that said, NASA, face up to it. And I didn't realize at that time that there were people who thought that the mountains, there's an image on Mars, there's some images taken of the surface of Mars, for which, under certain lighting conditions, a geological feature looks like a face. And these people were picketing to insist that we had gone black with the spacecraft because we'd made contact with somebody or the folks with the face on Mars. I didn't understand it at the time. I just thought they were kicking us while we were down. I thought, come on, we just lost a spacecraft. Only a few hours have gone by, and here you're telling us that we've got to face up to our inadequacies, I guess. That was my experience of the loss of the Mars observer. So Mars. This, get a...
Rating. Risk mode under parachute are 20 to 30.
This is an image of the surface of Mars. Actually, a video.
Dynamics phase. Come back again with risk mode dynamics.
Risk mode is nominal.
It's one of my favorite videos of the surface of Mars.
Valid range.
It's taken suspended under the world's largest supersonic parachute,
We've acquired the ground with the radar.
taken by the Marty imager.
Has separated. We've found the ground.
The Marty imager that's attached to the rover, and it's looking at the surface of Mars as we descend towards the surface. Pulling off such a video is difficult. It involves having a spacecraft successfully heading to the surface of Mars. That itself is difficult. We like to think, I think aerospace engineers, systems engineers, I'm a systems engineer, like to think of ourselves as sort of sometimes embodying the epitome of that act of synthesis of multiple different fields of endeavor and weaving it together into a systems solution. I think those of us who get involved in landing on Mars like to think that we're the epitome of that aerospace systems engineering act. Of course, we're wrong. That effort exists in all of our systems, be they hurtling towards Mars or delivering fresh water to a city. But I want to share with you, with perhaps some measure of pride, the efforts that we took and focus on a couple of different areas of our fantastic system that got Curiosity to the surface of Mars. So about 10:30 in the evening on the 5th of August for us in the West Coast, 1:30 in the morning out here in DC, we landed in 2012. When we did that, we were delivering the largest payload to the surface of Mars that we'd ever done. We were capable of reaching altitudes that we had never been capable of reaching. We were able to land more accurately than we could have ever before, and we could do this over a wide range of terrains present at the landing site. We were doing this, of course, by building on the efforts that our predecessors, starting with Viking and then Pathfinder and Mars exploration rovers, these missions had set up systems and a way of doing systems engineering that we were able to exploit to have this success. So I want to give you a little bit of an overview of the entry, descent, and landing system for Curiosity, and then speak to a couple of key areas that we needed to get right to be successful on the surface. I picked propulsion because it's sort of topical for Yvonne. And our propulsion system, we certainly would need to have a more capable system at Mars than we had ever placed at Mars. And we did that by developing something that we called the Mars Landing Engines, or MLEs, and I'll speak a little bit about that. We also needed to have an altimeter that would work, a fancy altimeter, and velocimeter. And so we developed a Ka-band, multi-beam, Doppler and ranging radar system, and I'll speak a little bit about that and some of the system-level challenges, not only challenges within the building of that, but the system-level challenges we had with the interaction with the surface. And then I think it's impossible for me to get away with, or should be impossible for me to get away with, speaking about the entry, descent, and landing system for Curiosity without talking about our touchdown system, the sky crane maneuver, which garners a lot of attention. And why would we do such a thing? So, as a primer of getting to the surface of Mars, if you're taking anything bigger than a bread box or smaller than a house, you kind of have to do 4 things to get to the surface of Mars. Maybe 5 if you count throwing away your ride. So the very first thing we do is we separate from the cruise stage. We head off to Mars with a solar array and a propulsion system, a cruise propulsion system. And that helps us change our trajectory en route and gets us right to the right spot at the top of the atmosphere of Mars at the right time. We discard that about 10 minutes prior to separation, and then actually, we experience what for me was the most agonizing part of the trip to Mars. There's about 9 minutes or so between when the entry, descent, and landing software ascends to prominence within the spacecraft and takes control over the spacecraft, and when we first touch the atmosphere. And we get essentially no data in that time. And that, on landing night, felt like a year. We're just sitting there waiting for the first message from the spacecraft that it's kissing the top of the atmosphere, it has some interaction with the top of the atmosphere. Intriguing piece of trivia, that first message was in error and stated, the very first piece of telemetry we got come across our screens landing night said, beta out of bounds catastrophic. Beta refers to the angle of attack, the slip angle of attack, and what it was a, we're just kissing the top of the atmosphere, so we have a very high signal to noise rate, very high noise to signal ratio. And it was a poorly conditioned sensor that was reading a slip that wasn't really there, and slip greater than 10 degrees was catastrophic. And that was the very, very first sign. And so all of us who were looking at the screens took a little breath in. Then nominal data came up, and we proceeded along nominally, and so we just, whew, okay. And after the fact, we figured out that it had been the zero conditioning, the calibration of that sensor, put it gave an error signal when it was submitted to just such a small signal from the initial kiss of the atmosphere. So you hit the atmosphere, you go through a heating and deceleration pulse. For MSL, we guided our way through that period of flight. So through heating, deceleration, and what is shown here is hypersonic maneuvering, through that whole period of flight, and I won't have a chance in our time to speak of it in much detail, but I'll just mention it here, we fly canted with a CG offset, as Viking did, as the Apollo and Gemini capsules did, and we steer that lift that is generated from that canted flight using a guidance algorithm that's actually derivative of the Apollo guidance algorithm. And that allowed us to take a 100-kilometer mist distance and knock it down to about 10-kilometer mist distance, which then allows you to open up a lot more spots to land on the surface of Mars, specifically the bottom of Gale Crater, which we wouldn't have been able to land if we hadn't done that. That deceleration takes you down to about Mach 2, and then you're sort of approaching the capsule terminal velocity. So we open up a parachute, and in our case, it's a very large parachute, the largest supersonic parachute that we've deployed in another planet. And that slows us down quite a bit to about a couple hundred meters a second. And at that point, we discard the heat shield, and we start looking for the surface with a radar. This is a Ka band pulse pair Doppler range and velocimetry, 6 beams, and we're looking for the surface to decide when we're going to let go of the parachute and go to powered flight. Entry, everybody has to do it if you're going to Mars. If it's bigger than a bread box, smaller than a house, you're going to use parachutes. Bigger than bread box, smaller than a house, parachutes aren't going to do everything you need to do, and you'll probably go to rockets. It's only when you get very small things that you can harden, a la artillery shells, that you can start to skip some of these things. We did that with the DS2 probe. We went just from entry all the way to the surface, but with a 30,000 G smack into the surface. Regular sized spacecraft don't like that. So at about a mile, 1.6 kilometers above the surface, we separate from the back shell. We perform a divert to get out of the way of the back shell, because when we light our engines and start to decelerate, we don't want to get smacked in the back of the head by the 500 kilogram back shell and 150 kilogram parachute. And then we perform this divert and delta V and come to a constant velocity above the surface, about 200 meters nominally above the surface. And we're looking straight down at the surface with our radar. And we perform a vertical flight down to 20 meters above the surface, 21 meters above the surface. At this point, we've slowed to about 3/4 of a meter second. Separate the two vehicles on tethers. It'll seem like it's a good idea later on. And we proceed downwards, and the descent stage, the propulsion backpack that the rover was wearing, which has an IMU in it, and is communicating with the flight computer, which is sitting in the rover via an umbilical. The descent stage continues to go at 3/4 of a meter second downward, dutifully. The rover's weight is taken up by the Martian surface, and we notice that the throttle settings have changed massively to maintain this 3/4 of a meter second downward velocity, and we disconnect from the rover and fly off to a safe distance to impact the surface. Another way of seeing this, picture's worth 1,000 words. Moving pictures, gazillions of words. I could have saved myself some time, but let's watch it. Looks like an animation. So here we are getting rid of a balance masses. We fly to Mars spinning, balanced state. We need that CG offset to fly endoatmospherically in an unbalanced state. We have a reaction control thruster system that steers that lift vector that's developed by the canted flight through the heating pulse, through the deceleration pulse, and we only, in fact, all the way to parachute deploy. There's a pulse switch monitor with MR107s for those who track. We then throw away more tungsten. Imbalance mass is then thrown away so that we can straighten up and fly right prior to parachute deployment. Discard the heat shield. Look for the surface. It's at this time when that beautiful movie that I started with is filmed. We have 8 Mars landing engines. They are Viking derivative. We'll speak some time about that. Viking-like combustion chambers and can't buy shell 405, so it's S405 by Aerojet. We have a little struggle. This is that Marty imager. This is the film, the digital video camera that was taking images that were reconstructed into the video I opened. Here we are 20 years below the surface. We're lowering the rover and deploying the ability. It never looks that smooth in reality. The two continue together. Confirm that we've touched down, cut free. Never get the guys doing this animation to show the boom. You know, and I didn't include, I have an image of the dust cloud of the boom, which we got, and I'm really now sorry I did not include that in this talk. So, delivering the rover, wheels down, kind of ready to start its surface mission, start its commissioning on the surface of Mars. So that is the MSL EDL in a nutshell. So now with that overview under our belts, let's take a look at a couple of subjects on the propulsion system. So the prop system, this is an image of the descent stage, that upper part that flies itself away, was for spacecraft going to Mars pretty big. Well, the rover was we were putting a big payload down. We carried about 400 kilos of hydrazine fuel, and you see those in the 3 tanks. I don't know if I've got a, thank you very much, I'd love that. One, two, 3 tanks and 2 hydrogen tanks helium tanks for pressurant. you can start to see it was quite an effort for us at the lab. We build propulsion systems, but we don't build propulsion systems of this size. This is sort of almost akin to a launch vehicle. It's not quite, but we learned a whole bunch of lessons that, for instance, prop lines, which are typically 1/4 inch or 3/8 of an inch, don't provide much structural stiffness and aren't usually included in the structural models. But our 1.25" prop lines actually provided meaningful load path, and we had to manage, for instance, load sharing between this very stiff propulsion structure, the stiff propulsion lines, and the structure itself. But to get this together, 3 key pieces were kind of needed. We needed to recover Viking heritage to make these MLEs. So we chose, I'll just speak to that in a second. We also need to be able to test this in a way that didn't cost an unacceptable amount of money. So we chose not to build an extra system and do a full system hot fire, but we chose to do piecemeal testing and analysis and string that story together. I'll briefly touch on that. And then from a system application level, we needed more dynamic range than a Viking engine would have provided us, than that combustion chamber would provide us. And so I'll talk about how we got that. It was really easy in the end. So the prop system continuing. For a little bit of scale, here you see some technicians in and around the propulsion system. Here you have the CAD image, and I just want to take a moment to say that it really was 2 propulsion systems. This is not uncommon. In one, it's an RCS system. These are the thrusters, MR107 thrusters, that are pulse width modulated and that we use during entry, but that we stop using prior to parachute deployment. And then the Mars landing engines, 8 of them, that's a pressure-regulated, throttled propulsion system, monoprop, hydrazine, that we use for, we call it the descent propulsion system we use for powered flight. Here they are again in their applications. It put us through our paces, the scale of this propulsion system, not only in the scale of the lines, but in the development. We had to develop or requalify. We used a pressure regulator from the space shuttle, and we had to requalify it for our application. We went in pyro valve development, tank development, engine development. We bit off a lot to chew. And one of the first struggles we had was with the Mars landing engines themselves and with the catalyst bed of the Viking style catalyst bed. There we go. So up here you see a workhorse development engine. When we sought out to start this, the propulsion system development, we said, we want to do a low risk, ideally low cost risk development. We had, as you know, is historically the case, been given a cost target that was uncomfortably below what was the natural cost that would come out of the grassroots costing, and we were left with that dynamic tension that everyone in the room who's ever worked on a spaceflight system has experienced. And one of our responses was to look towards a cost risk mitigation. We didn't want to develop an engine from scratch. We knew we needed a throttled engine because we were going to be at thrust levels that pulse width modulation would give us a structural dynamic nightmare. So we went with, we said, can we recover the Viking heritage? It just so happened to be that a gentleman named Carl Guernsey at the Jet Propulsion Laboratory, some of you may know, Carl certainly knew Yvonne and was friendly with her. Carl had a Viking engine under his desk. Not quite flight bonded stores, but it was the only specimen that we had. And we brought it out and we tested it. Not with the bell, not with the shower head bell that Viking had used to reduce the shears and pressures on the surface and reduce soil erosion of the surface, but with a single bell as is shown in this development engine. This is actually a development engine made with the same recipe and residual catalyst. And one of the first challenges that we found ourselves with was that we put, I've got a plot of the pressure drop within the cat bed across, with flow rate. And what we noticed was that the Viking engine and the first development unit acted in family. We went then to make a second, third, and fourth development engine, and they weren't acting the same at all. This was a head scratcher. We had noted that we had a batch of what was Shell 405, literally in a drawer somewhere, that had been used to, that was the right sieving, that had been used to put the Dev 1 engine together. But we were using S405, supposedly the same stuff, now made by Aerojet in 2000 and not made by Shell in 1968 or whenever that batch was. And they acted differently. In fact, even though they had the same grain size distribution, under microscopic inspection, the grain shapes were slightly different. They'd been rolled through the same process. People have been using this as a hydrazine, for hydrazine catalyst for years in many commercial thrusters successfully, but in our application, looking in the Viking cat bed, it didn't behave well. And it especially didn't behave well when we fed it cold fuel. We did that because some of the testing happened it was outdoor testing at the time, and some of the fuel was stored outdoor, and we tested in the summer in Auburn, outside of Sacramento, California, at Aerojet, and then we did testing in the winter. And so those two experiences had us retool the grain size distribution a bit of the S405, and also tighten down the flight temperature limits on the fuel. They had been plus or minus 20, 0 plus or minus 20, and rather 20 plus or minus 20, and they became 30 plus or minus 5. So we really made sure that that fuel was coming in warm and at a very tight temperature bound, so we could be comfortable that we'd get the life out of the engine and not break down the catalyst bed. Now with an engine that we thought would get the job done, we had to put together the story of how the whole propulsion system would come together. We did this again in piece parts. So we had a mock-up, a flow system test bench that we ran water through. We used this for both water hammer testing, again with water, for the RCS system, and also then for flow, stability, pressure drops through the filters and the pyro valves on the throttled side of the system. We did hot fire tests of the engines. We did tests with the throttle valves, but the whole system with the motor drive electronics driving the actual actuators that would drive the actual valves in the actual propulsion feed system was tested only once, and that was tested on August 5th on a mile above the surface of Gale Crater. I mention that because our prop guys are proud, and I think they're reasonably proud. There's a lot of talk nowadays of folks, and at NASA over the last 5 years has been very much the vogue to build propulsion systems of free flyers to demonstrate that you can do that, which is good. Our prop guys are pretty proud that they did it, but they didn't fly it around Earth. They just put it all together, slapped it, put it in a rocket, slapped it on the tush, and crossed their fingers. Now, the dynamic range. So a word, an interlude about landing, soft landing, hard landing, legged landers. The sky crane allows us, and I'll speak about this in a little bit more detail later in the presentation, but the sky crane allows us to do a real closed loop touchdown. And that's typically not done. Legged landers aren't closed loop. Legged landers, for a whole variety of reasons, which I won't enumerate, come in, compared to the sky crane, relatively hot, relatively fast, usually a couple of meters, 2 to 3 meters a second vertical, a meter a second horizontal. They come in quickly. They have a lot of shock absorbing in the legs. They slam into the surface, and during that slamming, spacecraft notices that it's run into something and terminates the closed loop, opens the loop, cuts the loop. There isn't a force feedback. There's not closed loop control taking place during the landing process. That's not the case for Apollo, where you have an astronaut, but it is the case for our autonomous landers. You don't need as much dynamic range when you're doing that, because you're never going to throttle down under control to those levels. You're going to come in, you're going to slam in, and you're going to cut. In fact, for instance, the Phoenix and now InSight propulsion systems and the Mars Polar Lander propulsion system cut power to the propulsion drivers when they see the signal of the touchdown trigger. So they're not changing the loop, they're terminating the loop. So because we're flying through the surface, we're in closed loop control, we needed a dynamic range of the thrusters of about 12 or 15 to 1. We needed to be able to have min throttle to max throttle greater than we could get out of the Viking engine. The Viking engine had about 6 to 1. It could go down safely to about 15% throttle before you get a catalyst, combustion chamber instability with the flow into the cat bed. We struggled with this a lot in the development, how we would solve this problem. The system development sort of solved the problem for us. We grow significantly enough in mass that when we started out with 4 engines, then we were at 6 engines, and eventually we were at 8 engines. And at 8 engines, we were able to seize the opportunity to shut down 4 of those when we got into the sky crane maneuver, when we were in proximity to the surface, and operate on the only remaining 4, and now those 4 were back up into a throttle range that was safe. This is, for those who are interested, the actual as-flown throttle settings for all 8 MLEs, and you can see when we go into sky crane, colors change. These drop out, these MLEs drop out, and we're just left with the corner MLEs operating. And this allowed us to get very fine control in that fine operation and yet have a nice, generous thrust to weight. We liked it to be a greater than 3 so that we wouldn't have lots of gravity losses and have to carry extra propellant to do our delta V when we first jumped onto the powered flight. Now, the radar, our altimeter, you need it. We had gone to Mars previously for Pathfinder, for Viking, used a 4 gigahertz wide beam velocimeter and range, Doppler and range. We had performed the Mars Pathfinder and the Mars Exploration Rover missions without using Doppler velocimetry, with just using range and range rate calculated after the fact, not by the radar instrument. We'd convinced ourselves that that was a bad idea, that as you looked to get softer and softer touchdowns, as you looked to have finer control, you needed that velocity measurement. We'd also convinced ourselves that using wide beam radars has a complex, and it's true, has a complex interaction with terrain. So a wide beam radar that is looking at a mountain, if you're coming straight down up on a mountain, the first return is dominated, the energy is initially dominated by the return from around the mountain. And so the ground appears to be far away from you at the base of the mountain. And as you come down and the beam picks up more and more and more of that mountain, you get a return that radically starts to grow. You're 100 meters above the surface, you're 70 meters above the surface, you're 20 meters above the surface, you're 4 meters above the surface. The surface comes up to get you. Alternatively, there's something called a mesa or a crater failure. If you're coming down into a crater, you can look at the crater. Again, you see the return from around the crater, and you're landing in the crater, and it's not until you get into the crater that the surface appears to recede from you. Now, if they don't recede or come to you too quickly, you could get past that, but it puts the navigation filter and the guidance navigation control system up for a big challenge to have a not necessarily monotonic signal about your altitude as you approach the surface, right? And there's very large discrepancy between your inertially navigated state and the terrain relative state. So we wanted to go with a 6-beam radar. We also had experienced radars that use past measurements as to improve the current measurement. That is to say, they're filtering inside the radar instrument themselves, and they're using, well, my last measurement said my range is a kilometer, so I'm not going to search all possible ranges. I'm going to go with the kilometer that I had before and try and improve on that. And we discovered that such systems also provide complex behavior and sometimes can get confused and never let go of the erroneous measurement. So we chose to design a system that would wake up afresh 20 times a second, and each measurement, it would start with no knowledge of any previous state, go through its range gating, discover where its range was, focus its range measurement at that range, focus its velocity measurement at that range, do that 20 times a second, and then move through the beams. And I'll talk about how that has an effect on the V&V. Also, we discovered well, I'll get to Sandy radar in a second. So, we cannot, well, here's a good picture. I want to get you through this. This is the actual picture of the radar, the little yellow-like pizza plates, maybe. There are on a proboscis. You can see the white body of the rover. This is the rover. Here are the wheels tucked up against itself. You can see the red removed before flight covers on the MLEs, our landing engines. So you've got a jet backpack kind of thing strapped to the rover. The rover's got its wheels up against it, and we've shoved it into the back shell. And hanging off of the descent stage on what we called a proboscis, on a strut structure, is this set of antennas that are used for the radar. Now, we make lots of mistakes, and when we're good, we learn from them. And the previous missions, Pathfinder, MER, Spirit and Opportunity, had taught us several things. And one of them was the importance of designing or architecting your system to be V&V-able. Like, don't design something that you cannot check, that you cannot verify. In fact, take it one step further. Design with an eye, architect with an eye for verification and validation, so that the residual risk that's left over, that validation process is simple. I mean, the best ones are by inspection, and that the risks that are left over are minimized when you are forced to architect your system so you don't need a lot of verification and validation. So we tried that with the rover, with the radar, and I will take you through that. So the radar has two very critical periods of operation. One, when we're finding the ground. If it lies to us at that point, we won't get off and into powered flight at the right place. We'll either get off much higher than we should, in which case we may well run out of fuel, because we'll start decelerating, and then at some time the radar decides to tell us the truth again, and we find we're a couple miles above the surface and we don't have a way to get there. So that's a very important place. Additionally, it was very important that it not lie to us when we were in this delicate sky crane mode. So we need to be able to test it. And we need to be able to test over a relatively wide range of operational conditions. So here's a plot of a subset of those operational conditions. What I plotted here is planet relative velocity, not necessarily the angle of incidence, and the altitude above the ground. And we have this portion of these trajectories are the range of altitude, velocity, space we can go through on the parachute, depending on the atmospheric conditions on the moment of arrival. And then here we are down into the region where we're in powered flight. And then we get way down here to essentially 1 meter a second or so. We're in the range where we're doing the sky crane maneuver. So we wanted to check the radar's function with respect to returning from real surfaces, Mars analogs that we would go out and scope in the Mojave Desert, over these range of dynamic conditions, which presented some measure of challenge. If you imagine if the radar had history to it, that is to say, if its measurements were based on previous measurements, then you're forced to follow trajectories to get good measurement data. You have to shape your test trajectory to be like your flight trajectory. So if I want to know how the radar is performing at this point, I had to have taken it through its performance at this point, its performance at this point, et cetera, et cetera, et cetera. By waking up afresh, even though it seemed like we spent a lot of time finding where we were, like we had no memory, doing that 20 times a second meant that I could make this measurement independent of how I got to that state in this space. Which also meant I could do things like put this radar, as we did, on the wing of an F-18. You know, we are on a parachute and we are slowing down and starting to point at the ground. So our Mars trajectory starts fast, slows down, and as it slows down, it starts to point at the ground. It's kind of the opposite of an F-18. An F-18, when you point it at the ground, it starts to speed up. In fact, that's what an F-18's trajectory, trying to give you this data point, in the F-18 points his nose at the ground. You go, hurry up, get that data point, because I got to pull out of this thing. But we could do cuts through these space that were actually almost orthogonal to the actual flight trajectory and still pick up the data that we needed because we had, at a basic RF function level, architected the radar to not need information about the trajectory to get the measurement. We also then did things like place the radar on a gimbal, all 6 beams on a gimbal, and spin it back and forth as we might if we were swinging underneath the parachute. You know, that video, you see some jostling going on. That's actually relatively mild jostling. We had to be prepared for the fact that it might be a very bad day. We might have plus or minus 60 degrees of swing on that back shell. And so tests like this, where this is a movie helicopter and a movie gimbal and an EM radar with an EM IMU and a set of laser rangefinders to get some ground truth. And we flew that helicopter for 47 days over various places in the Mojave Desert, collecting hundreds of times more data than we would use in a single flight to convince ourselves that the RF interaction over a range of ranges, range rates, and angular rates would all return the right kinds of answers. We did things like put an RF model of the rover underslung underneath the radar to make sure during the sky crane we wouldn't spoof off the rover or any of the deployments of the sky crane. We tested in ATLO, the actual radar, through the actual avionics system, hanging, and we actually pulled the crane up and down and confirmed that, yes, we're measuring the right range. In some of these tests, in the helicopter, we found a surprise. So here is what we called sandy weather. In a test that honestly wasn't exactly like flight conditions over the Cadiz dunes, we were hovering about 1 to 2 meters above the surface. And you can see the rotor wash was taking up a lot of sand and kicking up these ribbons of sand. We saw what we did not anticipate, a higher than anticipated error velocity measurement out of the radar. And we were immediately thrust into a question of whether we would experience this on Mars. So this was non-flight-like conditions. You're in a helicopter's rotor wash is not, at 1 atmosphere Earth, standard atmosphere is not the MLE thrust from 7.5 meters. But would it happen? And you can see here actually the accumulation of error as we get lower. So this is in meters from the surface. And as we're descending on the helicopter, you can see that the velocity error, now that may not seem like a lot to you guys. 1 meter of error measurement. I'm always impressed by how ambitiously we spec the requirements on our system. The radar was allowed 0.2 meters a second of error itself. We were allowed 0.5 meters a second of horizontal velocity before the rover would start to have hiccups. So this was too much for us to accept, and we had to step into this question about whether this would happen at Mars and what we should really rightfully expect. And that took us on a trip down memory lane. So it ends up being that this is not the first time somebody's asked this question. In the Apollo era, there was concern of visual obscuration of the landing site for the astronauts by dust being kicked up by the jet action. And this was looked again by Hutton for Viking. So we looked at this, brought this work back up, and developed a way to try and bound if this would happen at Mars. I'll take you through that. This will be the most technically laborious, so bear with me. I'm trying to cater to a wide range of possible audience members. So it ends up being, if you think about it, with a gas jet impinging on a unconsolidated broad spectrum granular material, broad spectrum grain size distribution, granular media, you will kick up and blow away dust. And how big the dust you blow away is a function of how hard you're blowing. Not too terribly complicated, and that's reflected here in this plot. And that's the work of the Apollo and Viking era engineers. That, it ends up being, has, the radar has a differential sensitivity to dust as a function of the size of the grain size of the dust. In fact, it's a strong function. It's d to the 4th, that return from a single granular particle. So what you see plotted here is actually at a given altitude, the descent stages at a given altitude, the material that's being kicked up, convolved with the radar sensitivity, gives you this curve. Here is the backscatter coefficient. And this peak is for that altitude, the worst dust that we can kick up. And that dust, again, is the convolution, not only the dust size sensitivity, but also the volume, the number of dust particles we can set up. So to try and bound this, we took curves at different altitudes. We picked the worst case dust grain at that altitude, and we constructed a curve of what the worst particle size was as we descended. And then we invented a dune, a clearly inconceivable dune, that was layered with this material. So it was layered with the worst sized dust. When we were at 10 meters above the surface, the part of the dune that we were then excavating had the dust that was the worst case for that part. And as we got lower, we threw that dust away and uncovered even worse dust that was perfectly sized for the dust that we could, our sensitivity at 7 meters, and so on and so forth. So it's, I hope, clearly inconceivable to find such terrain in nature, but it's a way, again, of bounding our way out of the problem. We then look at the range of possible backscatter coefficients that the surface itself, not the particles floating over it, but the surface itself can. And then we can construct a worst-case velocity error from these two. And that's this, and it's a function of what we assume, how bright we assume the background of Mars, how bright we assume the ground underneath the flowing dust is. So if the ground return beneath the flowing dust is weak, you get this curve here. It's minus 25 dB surface. Then we take this whole thing and we pass it through our navigation filter. And we ask, how badly would our horizontal velocity be poisoned when we eat this, what I hope is clear to you, inconceivably bad dust-poisoned radar measurement? And the answer is, we come up with 1/4 meter a second. So that's not meeting the requirements of the radar, but it is absolutely meeting our overall end-to-end requirements, and we had kept enough margin so that we were able to be comfortable going to Mars and potentially experiencing as much as 1/4 meter a second velocity error at touchdown due to blowing sand-induced radar velocity measurement error. So this is an example of failure. When you find yourself working this hard, you've done something wrong, right? There was an architecting thing that in hindsight, we probably should have picked not 35 gigahertz, but 13 or 7 or something. In other words, we really wanted narrow beams. That drove us to high frequencies. The high frequencies made us more sensitive to dust particles of the size that we'd be able to liberate. If we had been fully appreciative of this sandy radar phenomena when we were architecting in the beginning, we probably would have accepted slightly wider beams, a slightly lower frequency, with less sensitivity to the kinds of aeolian deposits that you might run into on the surface of Mars. You live and you learn. So last, I want to touch on the sky crane maneuver. It's a maneuver, it's not a thing. That's one thing I want to help you guys with. So now you'll be in the know. Sometimes people say the sky crane and they think it's like either the thing on top or maybe the two things together. It's the act. We actually called it direct placement in the room when we figured it out. There was about a dozen of us in the room trying to sort out, pull old ideas together and combine them with new ideas to come up with an idea. When we left that room, we called it direct placement, but very quickly everybody called it the sky crane. And I want to talk about what we promised it might do for us, and then talk about what it really did for us. So I think, do I show this movie again? I'll just do it real quickly, because if I hadn't narrated as, whoops, boop. So as I mentioned, it's a maneuver. This is the maneuver. From rover separation to flyaway, to the beginning of flyaway is called. We would struggle with that mobility deployer. Some of these phenomena are very testable, some of them are not. We tried to leverage architecture to divide the system into a part that's analyzable and a part that's testable. And that's actually one of the virtues that we believe we came to with the sky crane. But we didn't adopt the sky crane as the first thing. We kind of were backed into it. As Gentry Lee, a friend of mine and mentor, says, it was the least unacceptable solution that presented ourselves. We started because we'd had success in Pathfinder and MER with the airbag touchdown system, using airbags. In fact, that CAD is an invention of Tom Rivellini, one of our greats at the lab, who's now at Apple Corporation. Tom, searching for a topological solution that didn't require an intermediate structure. Pathfinder and MER had put rovers on the surface of Mars. Those rovers had been in a tetrahedral structure that had been wrapped in airbags. And the scaling of wrapping things in stuff, which is going to feel like it should be superlinear, right? Because you've got a R squared thing going on with surface area, and it is. The mass scaling of that means that we needed to ditch that intermediate structure, and we were already really having a hard time making the scaling work, just putting the airbags directly onto the rover. And in the end, it ends up being that there aren't any fibers that we have, us humans, that we can make fabrics out of, that could make airbags that would be strong enough to handle the kinds of impacts that a 900-kilo rover would require under the landing conditions that our previous systems would deliver. So we struck that. We knew we didn't like the legged lander. You know, we lost the Mars Polar Lander in 1999, beginning of 2000, December 99, I believe. And when we went back through the failure analysis of that, one of the things we reminded ourselves of is how potentially unstable a three-legged lander is on sloping terrain. And when you put a 900-kilo rover on top of such a thing, it becomes even more unstable. And one of the sort of level ones that MSL was trying to do was wide surface access over an ambitious set of terrain conditions. So those were out. We tried for a while to solve that stability problem with something we called the pallet. Oh, wait. There we go. I was wondering where my words went. Which was an evolutionary dead end. So the pallet takes the legged lander, adds more legs, spreads out the legs, and allows the belly to flop. So you smack in with your belly, and you cushion the payload, the rover, which is shown above, from the impact between the pallet and the rover. The problem with that was the propulsion system's down in there, and when you start to armor up the propulsion system so you won't rupture tanks and explode, or you have a system that's very, very, very heavy, and it wasn't making the mass trade. And so it was in the fall of 2013 that we got together with a whole bunch of folks, 2003. It has been a long time. And came up with this thing that we called direct placement in the room, but rapidly got the name of the Sky Crane. Now, the bummer about the Sky Crane, like these legged landers too, is you can't really test it on Earth. We can do analysis and simulation. This is one of a gazillion simulations, millions at least, that we did. We've concluded all the physics that we think are important in this computer simulation. This is a slope that's 25 degrees. It's the coefficient of friction so slippery that the rover cannot rove, and yet we can land her and she'll just slide down until she finds some feature and arrests her motion. Problem with computer simulations, of course, and that's probably every one of you knows, they will only answer the questions that you ask of them. So they do not protect you for sins of omission. If you forget a phenomena or a behavior and it's not in your simulation, the simulation is going to say, that doesn't make any sense. It'll just answer the answer that's appropriate for that subset of the universe in which you actually live in, where those phenomena are omitted. The idea of actually doing a real test was beyond the pale for us. What it would require, you'd be doing a free-flying test in a vacuum chamber, because you'd want to get the real engines going. You really can't solve the gravity problem in a vacuum chamber. I suppose you could put the vacuum chamber on a very large kinematic arrangement and do some, but I'm joking, of course. It's not feasible. And so we looked, one of the features that we really liked about this touchdown system, the Sky Crane, was that we believed it cleaved the touchdown event into a set of phenomena that were analyzable, that we believe we should have confidence in the analysis result, and a set of phenomena which are testable. So let's talk about that. This is a great one. This is a verbatim. Actually, I added the two, analyzable and testable. But other than that, this is circa 2004, 2005, Sky Crane. I keep this around to remind myself of what we promised, right? It didn't say the promise. It just says Sky Crane architecture in 2004. I added the promise. So the thing about the two-body architecture is the following. It keeps the closed-loop control element high above the surface, where pressures from exhaust interaction with the surface, which the surface you'll never know, so you'll never know what that pressure field is, you'll never know the time evolution of that pressure field is. You'll have an unanswered question that you'll try and sweep under the rug saying it's small, but if you put yourself 7 meters above the surface or 8 meters above the surface, that small is a hell of a lot smaller. That's a thing. The tension-only bridles that connect the rover to the descent stage coalesce at a point that's very close to, we tried to make it identical, but naturally that will never be, but very close to the center of gravity of the descent stage. So the forces that the rover's surface interaction generates are a waning force that is, there's also 7 meters, 7.5 meters between those two vehicles. So you can fall off of a 2-meter rock or a 2-meter high rock. You can fall one side or the other, 1 meter or the other, and the angle of that force, the change of the angle of that force as it wanes is very small. So no torques, no meaningful torques. The forces are all in basically the same direction. They all do one thing, which is get smaller. They're not necessarily monotonic. You can imagine crazy landing situations where you come off a rock and bounce and do something like this, and so they can have some signature to them. But when you're moving downwards at 3/4 of a meter a second, it ends up being they wane very quickly. So the control element of the spacecraft gets to kind of virtually fly through the surface of Mars. It's been told to go 3/4 of a meter a second down, 0 horizontal velocity. It does that. And the rover has a boundary condition above it that's very evocative to a crane here on Earth. I can turn around and I can hook this rover on these set of bridles to a crane on Earth, and I can say, hey, crane, operator, go down at 3/4 of a meter a second. And the test that results out of this, the rover's surface interaction, although poisoned by the fact that gravity is 3 times as much, approximately, here on Earth than it is at Mars, but the test that results is not further poisoned by the closed-loop interaction or the vagaries of how the controller may work. So, we loved it. It did give us some things to test. All of the GNC stuff was done by analysis. We did no testing of pressures. We did no testing and all of the mechanical deployments, both the lowering of the rover, which was done by an electromechanical brake and driving some resistors, and the deployments of the rovers we could test, and we tested here on Earth. And let me show you some test videos. Those, in the animations, it's a beautiful, gentle release of the rover's mobility system. It's not that in practice. In fact, it was so not easy, not gentle, that we ended up finding quite late that we were driving some of the load cases of the mobility design simply by the impacts from those deployments. That one gets, the wheels are missing there because we didn't break the mobility system, and gravity's 3 times the height. You can test these things. You still have to do a lot of analysis because your inertias are wrong, your masses are wrong, your gravity's wrong. You're trying to do inertial forces and gravitational forces and get those things balanced or understood correctly. Interesting side note, stress analysis, I don't know how many structural analysts are sitting in the room here. Stress analysis is always a very conservative, almost uniformly, because we follow best practices. And those best practices guarantee a conservative outcome. For instance, one of the things we do, we say perfectly elastic, perfectly plastic behavior. I mean, usually, not many of us do the strain hardening curves in our stress analysis. That's like crazy, right? So we predicted that we would break the mobility system, and we couldn't, with even like elastic, strain hardening, nonlinear stress analysis, prove ourselves comfortable enough to not do a test. So we broke down, pulled apart our EM mobility system, hooked it up to hydraulic jacks. We thought it would fail at 1.2 times the flight limit load. At 2.7 times the flight limit load, we ran out of stroke in the hydraulic jacks because of the beautiful nonlinear load sharing. We went plastic, the structure becomes a geometrically nonlinear, load goes into other places, and it ends up being that we were in fine shape, and we convinced ourselves that we'd be comfortable going to Mars like that. We can also test, and did test, this is the most dramatic of those, the touchdown system, the wheels themselves.
Vertical velocity of minus 82.8 meters per second. Start enabled.
Sorry, I don't want to go there. I want to... That's on a steel plate. And it's on a steel plate so that we have very low friction, so that we get a lot of bouncing, so we can see how bad that bouncing is. Watch the loading and the dynamics. Again, they're not exactly as they are on Mars. This is a scaled test. We have to scale velocity. Time is scaled because of the acceleration. But as it would come to pass, the Sky Crane delivered on all of those promises. It really allowed us, we thought, by all of our analysis and all of our test techniques, it allowed us to deliver this big rover to the surface of Mars. But unfortunately, the real proof of the pudding would only be
Vertical velocity of minus 82.8 meters per second. Start enabled. Standing by for Batel separation.
$2.5 billion, you know, who's counting?
Signaled Odyssey is still strong.
A decade of most people's lives. Again,
We are in powered flight.
so you'll watch, the image gets a little more steady when we're in powered flight. The audio, we've done our best job, put the audio synced with the visual, but
About
it's
70 meters per
a
second.
little off at times.
Signaled Odyssey remains
Down to 50
It's
meters per second.
lagging a little bit.
500 meters in altitude.
You'll see us kick up. We're now in no, not quite
Standing
yet.
by for Sky Crane.
So that's our attitude maneuvers as we do
Constant
our
velocity
divert.
accordion
Now we're in
nominal.
straight vertical flight. You'll
Altitude
see us
error,
start to kick up
5.9
sand.
meters.
Kick up sand.
We found a nice flat place. We're coming in ready for
60
Sky
meters
Crane.
above the surface, we started to do that.
Down to 10
And
meters
you'll
per
see,
second.
now we're in
40 meters
Sky
altitude.
Crane. There, you see the wheel deployment of the mobility system.
Sky Crane has started. Descending at about 0.75 meters per second.
We had a
as
triple
expected.
check before we
Expecting throttle
announced
cut shortly.
that we were safe.
Signaled Odyssey remains strong.
Had to have a touchdown nominal.
Tango Delta nominal.
Which is, we didn't want to say touchdown nominal because we didn't want the world to think that we'd said touchdown nominal. So
You feel calm. Configure.
RIMU stable.
Telemetry.
RIMU stable was the second. That's
RIMU
the rover
stable.
IMU, so we're not dragging the rover around.
UHF is good.
UHF.
Touchdown confirmed. We're safe on Mars.
We wanted the antenna. The UHF antenna stood proud of the rest of the rover. So there were three real modes that we might fail. We might slam the vehicle down in a way that was unrecoverable. Tango Delta nominal, touchdown nominal, postcard, an event record from the spacecraft that said, I just touched down, and I think it touched down in a nominal condition. That was the first one, so we don't think we slammed the vehicle down. The second was that we weren't dragging the vehicle, right? So the rover IMU is giving us, I'm at rest. Okay, good, that's RIMU stable. The final one was UHF, we watched just the signal strength of that UHF antenna because the next possible thing was we cut ourselves free, go to fly away, and land back on the rover, crushing. And the first thing we would have damaged was that quad helix. UHF, we looked for 10 seconds of persistence on the UHF signal. After that, we called it, and the rest was history. So, in Epilogue, how did it really go? So let me take you through, I won't labor you through all of these numbers, but let's just do it like this. Green is good. Yellow is maybe worth talking about. Red is definitely worth talking about. So these are our pre-flight predictions. And if we're within 1 sigma of the pre-flight prediction, that's awesome. If we're within 2, you know, that might be forgivable if we have some understanding, but we should have a conversation. And then if we're greater than 2, then we really, what was up? Was our pre-flight prediction wrong? Was the flight odd? So everything, I'll tell you, doesn't really show up so great, is green, except for this, I'll walk you through. We got yellow on our heating. Our aerothermal heating is a source of tremendous uncertainty. The interaction with the TPS, the thermal protection material, can have an influence on the heating. Turbulence, roughness of the surface. And as dutiful engineers, at each fork in the road at each uncertainty spot where we don't know, and we could choose a unconservative or a conservative assumption. We dutifully and appropriately choose the conservative assumption. So when you find fields of engineering where there's a lot of uncertainty and yet people can get the job done, typically there may be a lot of embedded conservatism, because there'll be a lot of those forks in the road, and each engineer will recursively take the conservative one. We thought it would be 260, it was 110. That was pretty conservative. Come down here, our radar. This 0.7 meter second, I don't know if you caught that, I think it's in the first video. The engineer, Fred Sericchio, who called out, whose job was to call that, notice that and call that out, could not hide his glee. He says, radar converged at an error of 0.7 meters a second. We thought it would be maybe a factor of 10 above that. But that, again, that factor was our conservatism. We were using, for the factor of 10, we were using a worst case backscatter from Mars. That estimate was using a dark Mars and a very viciously swinging spacecraft. And neither of those came to pass, and we got much better. Here, fuel usage. Again, we're using an ISP on our monoprop, throttleable monoprop, because we don't sit all the way at max throttle, and the ISP, it's not, I think we used 215, and we saw better. And that's one of the reasons that we see up here a 2 sigma greater than, we use less fuel than we thought. We thought this number would be up around 310. And 260, although that's not that big difference, it was a difference for us. But the one I really want to talk about is the final and best lesson we got. So this red one here, which is our touchdown velocity. So our nominal touchdown velocity was supposed to be 3/4 of a meter a second, 0.75 meters a second. And we did a lot of analysis, including Monte Carlo computer simulation, where we took over 3,000 different input variables, and we debated vigorously how we should treat each one of those input variables, whether the distribution of uncertainty should be Gaussian or uniform or triangular, what measurement or test data we should use to inform the uncertainty, what fundamental physics would drive the process. We varied all of those 3,600 some odd, but we didn't vary surface gravity. We thought of all the things at Mars, we would be certain that we would know what the surface gravity at the site was to within 1 part in, let's say, 10,000, because we've got orbiters that have been mapping the gravity field of Mars for a long time. We used a 2-mode model, a 16-mode model, and an 89-mode model, and we saw no difference in our performance across those. And so we took the 2-mode model, we put that on board in the spacecraft. 2 pieces of pride before the fall. One, that we know that the surface gravity to that kind of accuracy. And 2, in our radar development, we ran into a problem with near field. When we were getting those narrow beams, those beams were 3 degrees apart, beam width of 3 degrees. When we were getting those, we were wrong about how far we needed to go before we would establish that tight field. And we became nervous about the near field interaction with some of our hardware. And so that drove our beam configuration, kept us away from using beams that might interfere with the rover. Before we had an EM and before we could hang a rover model, we had omitted using beams that could possibly interact with the rover. So we had just 2 beams. We called them the sky crane beams, and they looked way out in front of the spacecraft, so they wouldn't be interfered with by any of the near field. That means we were measuring 2 of our 3 components of velocity that we wished to control during the sky crane. The third, we dead reckoned using surface gravity. Well, it ends up being that there's a gravity anomaly at the Gale crater on the surface of Mars. That gravity anomaly is 400 microGs, and though that doesn't seem like a lot, we spend 15 seconds in the sky crane mode. You're accumulating all of that error. Actually, we're accumulating the error. You can see that gravity anomaly show up as we approach. Before we're even on powered flight, you can see the gravity anomaly take off. So, and it wasn't in any of our models. In fact, that would be acceptable if there weren't any models in human hands that did have it. Unfortunately, there was a model made by Australians that uses a different technique to develop the gravity model, and it demonstrated 300 micro-Gs of what the 400 measured 400 micro-G uncertainty. And had we known that that model existed, and we interrogated that model, we may have either put a better estimate of surface gravity in the model or put an uncertainty in the surface gravity into our appreciation of the system, and we wouldn't have been surprised. So now that surprise seems pretty small, right? We were targeting 3/4 of a meter a second. Our 3 sigma was 0.1, so we thought we would be 0.65 all the way up to 0.85, and we were 0.6. This slide is actually slightly old. The final number is 0.63. So we were only 2 centimeters a second off, but those 2 centimeters a second represent, because actually our distributions were not Gaussian, a Gaussian equivalent of like 5 sigma. That doesn't happen, right? Things, when you have a model that shows you some 5 sigma event happens, your model's wrong. It's not that unlikely. It's much more likely that your model's wrong that such an unusual occurrence has happened. So at any rate, and very thankfully, the fates gave us that error, that velocity error, in the slow direction. That anomaly could have had a different sense to it. We could have come down at 0.87 meters a second, and then every time something went wrong with the rover, the guys would point at the landing guys and say, see, you landed us too hard, you busted something. It didn't happen. So we were lucky. We were good. We were standing on the shoulders of giants, certainly. We were pretty good, and we were also had the fates on our side. So a couple of acknowledgments. Certainly this is the work of about 150 people. That's one of the things I cherish most in engineering, is that it's really a collaborative art. Some of whom I am directly stealing from and can be mentioned there on the reference page. And naturally, this work was all done by your tax dollars, and we appreciate that. Thank you very much. And now we've got some time maybe for questions. Yes? Yes, Steve. Yes, interesting question. So you mean from pebbles and stuff? Yeah. So we spent a lot of time thinking about that sandy radar problem and how much dust we kick up. In fact, relish sharing our dirty laundry. We messed up. We had architected this distance, the bridle distance, 7.5 meters, such that the flow conditions when the plume intersected the ground would be those that Viking had experienced during its landing. That was the approach. Now, it ends up being that from a fluid mechanics perspective, that fluid mechanics problem is quite hard. It's complicated. Starting with a jet, and you're asking the conditions of that jet 100 nozzle diameters downstream. It's quite easy to get numerical viscosity into your solutions and underpredict that condition. And we did that 3 times. We did it with our first model, we did it with our second models, we did it with our third models, and it was only when we were Ving our final model that we found and discovered, which was maybe lengthen the bridles to get them to the condition that we wanted. By the way, a 20-meter-long bridle. Not inconceivable, actually not inconceivable, but we had already built the spool and the motor and and the fuel, right, that would take, that descent would take, we would have to do sort of some major rework, or accept that we're going to kick up more sand, aspire to when we started. We did an analysis to say, could we kill the rover? What level of sand being piled on the rover would be deadly? If we looked even thermally was a big concern, right? Could we cook the rover? Could we put enough sand? If the rover woke up and had 1.5 inches of sand on it, would it overheat? We looked at the sand, erosion of the paint, and all sorts of things. And when you look at them, you would be, we had with quite a percentage. Now, what we didn't do in that analysis, through all of the sandy radar analysis, all of that excavation analysis, is ask, what are the biggest chunks we can liberate? And we didn't. That question doesn't close, it's ill posed, because it ends up being that how you get the real big dynamic pressure, liberate large stuff, is by surface irregularities and the evolution of generated surface irregularity, cratering, right? You start out with a plane, you have nice sort of saltation flow until you get fluid pressures that exceed the bearing stress, and then you get a slumping phenomenon. And now you have a little collector, and all of a sudden the pressures go up, and you start to excavate a whole bunch of material. So understanding what soil is, that behavior is soil dependent, very small, fine parameters in soil. Trying to ask that question, right? Got an answer. Inch-size pebbles you could toss up, because we'd actually busted up, I think, thoroughly, a conglomerate at the landing site, and so it heaved and now made reflectors and things that could pop big stuff up. We broke one of the hot wire anemometers on one of the wind measuring device. One of the instruments, the signal we were talking about big stuff. Yes?
Yeah, I'm impressed by your modeling and how you reproduce the noise that was generated by that vehicle at high altitude in your video. Where did that noise get recorded and what reality is it?
No, that whole movie is an artist's rendition.
But my suggestion is that you actually make it correct, because I think that there's a great deal of misinformation going around about noise in space.
Okay, I mean, if you're announcing that you're an advocate for a Mars microphone, you'll find many people in this audience, including myself, who share your advocacy.
No, I'm just saying that the movie is going to have noise in it, it's understandable. I'm sure that microphone might be that would be recording that noise, because if you cross, it's the noise that is propagates in space.
Yes. Well, it's funny. There's a double-edged sword with an animation, because you're giving one particular part to it. You didn't ask the question, which is, where's the cameraman? Which is an electromagnetic radiation analog of the question you mentioned, which is, who is flying alongside of the spacecraft or checking that anymore? And for this audience, it's not that bad because we pretty much figured that out. But for general audiences, people will come away with like, how did you make that? So there's no other person on Mars, and that's just a movie. And it's the mind's eye, the same way that the blue creatures in James Cameron's movie did whatever they did. But yeah, that's the double-edged sword of that. But what are those tools? Those are tools, and they've got two edges to the sword. To try and help the non-technical get an understanding. And you're right, they are incorrect, certainly incorrect when we're exo-atmospheric. And actually, of course, they're really incorrect. Well, I don't even know what this. I mean, actually, I do know what the repulsors sound like, and I do know what the rockets, the MLEs sound like, but those actually aren't that far off. The whole propagation through the atmosphere goes to a fair point. Other questions? Yes?
Looking at total effort, what do you estimate was additional effort that replaced testing, some factor of effort and cost that you had to incur with testing?
very, very hard question for me to answer because it's so it died into the wall of our thing.
Let me ask this. You talk a lot about trying to get to sit down and have not down drag out about what issues you were facing.
Yeah.
What impact on the schedule is that?
Well, so entry descent landing is a very awesome job to have because you wield this incredible club. Because all of the faults result in complete loss of mission. You and the team has this sort of, I didn't realize at the time. Right now I'm working on a sampling system for the next surface mission to Mars. And it's a different story. I'm the same guy, I have the same attitude, but it doesn't work like it used to work, right? Because death awaits you at every juncture. And it's not like, oh, we're going to be operational inefficient, or oh, the sampling's going to take twice as long. No, it's death. we don't have to do that. I mean, we could die. So, so because of that, I think our skids were and are historically well greased. Because of that, we actually were kind of ahead of the rest of the mission's development. Because we poured a lot of human capital, a lot of dollars up front. Before we were even a mission concept review, there was something called the Mars Focused Technology Program. And NASA spent $89 million, 81, 89, something, less than 90, but more than 80 million bucks, 3 years prior to the start. Things like that aerojet tests with the development engine and trying to recover the combustion chamber heritage of Viking was done. We spent $10 million of tech funds on that before the mission concept review for MSL. So we had a large forward investment. We attracted or prescribed what the lab thought were the best staff to do the job. And so I'm not really answering your question. You're asking, but we didn't lag behind because of those questions or beating on what you would work on. We tried to stay way in front and sort of overdo it. Because again, death is the other option, and so people are willing to have you do a really, really, really good job, which is great.
I think we have time for one more question, please.
Yes, sir.
Given what you've learned during this phase, especially where your model deviated from reality, what are the biggest lessons learned for future missions and the implications that might have?
Right. Old guy at the lab, he's not anymore, Frank Batel. And Frank Batel, this is very positive. Frank's very famous for saying this. It's not the thing you talk about that's going to get you. It's the thing you're not talking about. It's also one of those like smart bomb sayings because it forces a constant like hyper vigilant looking over your shoulder because okay, now I'm talking about that, so that's not going to get me. It's that other thing that I'm not talking about. What is that thing I'm not talking about? That's true. It's the thing you're not talking about. For instance, it's surface gravity. It's not that the wind models, that the 4 mesoscale wind models made by 2 different institutions and debated by a council, what we call the Council of Atmospheres, atmospheric scientists, are going to be wrong. It's not that thing, it's the thing you're not talking about. Now the problem is I don't have an algorithm for finding the thing you're not talking about. We did experiment. Actually, the DL team experimented with those things. How to say this? Without implying something's not true. Ways of altering your consciousness. I don't mean mind-altering substances. I mean mind-altering behaviors. Like, okay, this side of the room is bad guys, and these side, you break, tell me why it's gonna break, but you tell me why. You know, those kinds of intellectual exercises. And sometimes we're gonna go and eat lunch and have a good time and not think about it and hope that things pop into our head that way also. So we looked at different kinds of structured brainstorming techniques to try and find the thing that we're not talking about. Interestingly, surface gravity never came out of it. And in hindsight, it seems so painfully obvious. So keep trying to find the thing you're not talking about. Listen to all your people. Listen to your review boards. One thing I think you did a good job at, and I feel pretty, maybe the only reason I should be proud. There's in aerospace, there could be a wide range of relationships between it to the review process. And some people who I work with don't like it. They think that it's a trial. They do want to get us, they kind of want to armor up, get through the thing, and be done. And we looked at the review process as these guys are coming to work for us. And they're smart, and they have experience, and we're going to try and listen to them. We still didn't listen to them all the time. In fact, these famous not listening, so we won't go into the story, but talk about afterwards. So, be humble, listen to the people in your team, your review community, try and find the real gems that are in there. That might be hidden, either poorly transmitted, and try and think about that thing that you're not thinking about.
So before you stop, did one of the students have a question?
What you do is two questions. Yes, sir.
Would you do the same method again?
Would we?
Yes.
Yes, we are. So we return this. One of my proteges, very capable gentleman by the name of Alan Chen, is now at the helm of the Intercept Landing Team for the Mars 2020 mission, which launches in 2020 and lands in 2021. It will take a carbon copy of the Curiosity rover, except we're pulling out the science instruments and we're putting a sample acquisition system that I'm working on right now in the front of the rover. And we will probably, I think Alan will try to promote, and I encourage him to, some added capabilities to this EDL system to make it better. What we're doing, yeah. In fact, part of the reason we could is because we have enough spare parts that we can bring the price down.
Adam, what about scaling? How much bigger can you scale this?
Great question, John. Thank you. So there's two. When one says scaling, you could be thinking about architecturally or in terms of design space. So architecturally, I don't think that there's any limits to this approach. In other words, a propulsion system with a tensionally stable tensional relationship to the payload could happen at this level or could happen as big as the house is. At a design level, let me say one more thing. This system really works very well when you're going to terrain that's could be quite complicated. See, the rover could land at 35, 40-degree slopes. So you could never touch down a leg land on a 40-degree slope. It's not going to happen. So this kind of approach allows you to go to a wide range of terrain. Now, if you're landing something as big as a house and it's got human beings in it, and I'm one of those human beings, I don't want to be landing on a 40-degree slope. I want to be landing on a parking lot that has "Welcome Adam" already. And robots have made that preparation. There's an espresso machine. Wait for me when I get there, right? And so it may not be that this is the right landing system for that, not because of scale-related things, but because the applications are limited. I hope the first astronauts aren't like, whoa, I guess we can do it here. Now, in terms of design, there's some discretization that you have to do. I talked about getting the dynamic range weighted by shutting down 4 MLAs. Well, if we got, so the rover's 900 kilos, it ends up being at the descent stage, when we're in the sky crane, about 900 kilos, so you're about the same mass. That's nice. It's got a nice, crisp, big signature for touchdown. One of the beauties of the system that we designed. design is that you don't measure the touchdown event. You measure the persistent post-touchdown state of the spacecraft. So the descent stage has been told, you move 3/4 of a meter second down, I don't want to hear anything about it. And it's doing that. And all of a sudden it says, we have sort of a super ego that rides above it. It says, hey, look at that. The throttle settings are at half what they used to be. Wait a second. Let me check that again. Yep, they're still at half what they used to be. Okay, I'm going to check it a third time. Yep, still at half what they used to be. And now I have this persistent, the descent stage is still going downward. We've got little clock springs that wheel up the slack so we don't, put the cable all over the rover. And say, okay, yay, verily, the only way that we can have lost half the mass of the spacecraft persistently, well, I don't care what it is, because I'm going to assume it's that the Mars is taking up away the rover, I'm going to have myself ready to fly out. If you imagine the rover getting smaller and smaller and smaller, or this mass ratio getting different, that signature becomes in danger. If you imagine shrinking the thing down, if you got down to half, let's say 500 kilo, let's say 300 kilo rover, and now the descent stage is 300 kilos, now those MLEs are way oversized, and now we're down in the throttle range where we can't operate. So you need to spool an engine development, or use a different engine. Yeah, but you can't throttle down the form. See, we got this dynamic range between high thrust and vernier control by throwing away the form and operating the final form in a higher throttle range when we needed fine control. If you only had a single set of thrusters, you couldn't get down, and they were stymied with the dynamic range here, you couldn't get down below about 15% throttle. And you'd want that to do a sky crane. So you'd want, I think, double sets of engines, or deeply throttling engines that can go down to, let's say, 5% throttle. If you can get a 20-to-1 engine, then you can, but so there's a whole bunch of do it again with a different size rover questions that are design oriented, not architecture oriented, like that.
What about the aeroshell? Does that scale?
They scale, they all are not, these things are all nonlinear scalings, right? The aeroshell mass goes up, it's a wrapper, it's going to be an R-squared thing, except it's a plate that's taking pressure. And, the load path, for those who want to know, during entry, it's just ridiculous. It's heat shield, up around that shell, grab hold of the payload. So the payload's not touching the heat shield, and the flow's going like a bell clang. So those are all plate bending things, which are also nonlinear scale. Stiffness is scaled nonlinear weak length. So, for instance, see if I can remember this correctly. Well, here's things I can remember accurately. MER, I was working on MER, entered 840 kilos. It was 2.65 meter aeroshell. Most of that, we landed 500, so it was down around 200 kilos for the aeroshell. It's 850 kilos for the aeroshell on SL. So we doubled the size, 2.6 to not quite double the size, and we quadrupled, so you can see the nonlinearity in scaling. So there's nonlinear scaling that are going on. And someplace, you probably need to start getting better load paths. It's not such a big deal when your aeroshell's like this, but when your aeroshell becomes close to the size of this room, then you probably don't want to take it all in plate bending, up through shell, through the thrust cone, and back down. You probably want to let the loads go straight into the aeroshell. And then you've got a different kind of scaling going on. And I have a parachute scale through.
I'm going to ask for another question from a student. We're right here at the back. If not, no student?
Yes.
There we go.
Which part of the EDL sequence were you personally most concerned about failing?
Right, so the trite answer I gave to everybody who asked me that question in the weeks, months, and days, and hours, and minutes, as language coach, was the thing I'm most worried about is the thing I don't really get worried about. But it was actually true. So we had this process within the team where we had a risk parking lot. Anybody could come up with any wacky idea of something that could be a risk, throw it on a parking lot. We then work it as a team. itself to be a real risk or not. And then I had a budget in the back of my head where we would work it down till we believed it was 0.25% probability of failure. And then we stopped working it because now we're way into this noise. We're down in the noise floor of our building to believe that we know what the percentages are. And I knew that it would be acceptable if we had something like 95% probability of success. And so that gave me 20 some odd things that could be found like this that we could work down to 0.25%. So that worked out. The most risky thing, the absolute, without a doubt, the most risky thing, John just asked a question about it, was the parachute. So you can do engineering analysis, reliability analysis, all sorts of stuff that can convince you that most of the systems are 1 in 1,000, 1 in 10,000, that the computer will work out, that your thruster valve will stick, right? Those are way down there. It's hard to do that credibly with our parachute in our application and get anything better than 1 in 50 or 1 in 100. So in terms of single device reliability, the parachute dominates. Everything else is maybe an order of magnitude more reliable. Except for that thing you're not thinking about, because you don't have any idea what the reliability that is. Yes? Well, yeah, you asked.
The last question.
So, my question to you is, what technology do you not have available to you? For those of us who can help influence how technology should be developed, what did you learn? What did you wish you could have brought up? A frictionless gear or a very, very lightweight blanket?
No, very high performance, rad hard, computer CPU chips, FPGAs.
Really?
Yep. We were using a PowerPC 750 chip, which when I was a PhD student, was what powered my Macintosh G4, which was all the rage in the 90s. But that's what we're using here, right? That's right. This phone has 10 times the computational power of the spacecraft. We got away okay with it in PDL because we made choices totally based on that, right? Architectural choices based on that. But for instance, we couldn't do and didn't choose to do any massive visual processing, taking images and using image correlation to do any kind of processing, which, by the way, is an option available to you, but you need to have a Vertex V5 or something, which they can make rad hardened, but that rad hardened line was recently threatened to be discontinued. So the application, there's not a lot of folks who want to use high performance computing in the rad hard environment. 30 years ago, the US government kind of wanted to do that when we thought that like the nuclear threat was a big part of it. It seems that maybe we don't because we don't seem to be supporting that. And so the commercial applications for Earth orbiters is not the same. So we're not in that same use pool. So electronic equipment, especially large and high-powered processors that are rad hard, happening in the future.
I'm afraid I'm going to have to cut off the questions here, but you're going to have an opportunity to talk with Adam during the reception. Let me encourage you to do that. So, Adam, thank you again. Is to introduce a friend who's going to give the final remarks. A friend whom I watched come into the Department of Aerospace Engineering as an assistant professor and who executed a meteoric rise through the professorships to become department chair of the Department of Aerospace Engineering at Maryland, and to become the Fafardin Professor and Dean of the Clark School of Engineering at the University of Maryland. It's a pleasure to introduce Dean Darrell Pike.
Thank you, John. I sat there and I did not know Miss Yvonne Brill, but I learned a lot today from the family members who were here. Are the family members still here? Can we give them a round of applause? Thank you, Matt, for being here today. To all of her friends and colleagues, you've said some really wonderful things about Yvonne, and I think this seminar is an embodiment of what she was all about. We just heard a talk on the Mars entry and landing process and how innovative that was. And if you listen to the people who spoke about Yvonne and how innovative she was, so it dovetails very well. So in some sense, she was a master engineer, someone who created something that hadn't been before, a propulsion system, a patent for that propulsion system that I hope, Adam, was used on your system. At least some semblance of the design were evolutionary related to her patent. I think it dovetails very well. So she was a master engineer, someone we should celebrate, and we have celebrated today. And Adam, you look like an emerging master engineer. And so I wanted to say that as well. You mentioned that some of the scary parts of your problem were some of the unknowns. And I know another famous person, Secretary of Defense Rumsfeld, used to say, the unknown unknowns. So it's sort of very similar to what you're saying. And it's very true technically, that there are things that we just don't know and don't know about. But we hope that we have a little bit of luck when we're doing our engineering problems. So this is about engineering. And if you don't love engineering from having listened to Adam's talk, I don't know what to do with you, because this was an exciting talk. I mean, this is what it's all about. This is why many of us went into aerospace engineering. And I'm an aerospace engineer, so I know exactly what this is all about. And Adam, I really enjoyed your talk. And I think Yvonne would have been proud to have you as her inaugural seminar speaker. And I know we should, so let's give Adam another round of applause. And it's unfortunate that she's not here to share this wonderful day with all of us. But we are here to motivate the next generation, which are sitting in the back of the room. And I think, Adam, you've done that very well. And if those who haven't heard the story, the great story of Yvonne, and how she is such a special human being, and how she touched the lives of many women and many engineers in our community, not just here at the National Academy, but around this country. I mean, I have to say this because I was talking to President Dan Moat of the National Academy. I believe we may call her possibly the first rocket scientist and engineer, first woman rocket scientist and engineer. I think that's a phrase I'm probably going to use in the future when I speak very proudly about her. And another thing I was talking to President Moat about, and I'm not sure where the quote comes from, so you can correct me, President Moat, but I believe when she received her 2010 Invention of the Year Award from the National Inventors Association, that she or someone came to the podium and said the following. You can correct me if I'm wrong. It took 3 men to invent, was it 6 men? Now, wow, the number grows. I haven't even finished the remark. It was 6 men, it took 6 men to invent the Post-it note. But it took 1 woman to invent a propulsion system. So if that isn't an inspiration for you, I don't know what is. So to the women in the room who are students at College Park, remember that quote, and you'll be inspired forever. So let's have a reception outside. First of all, I want to thank one other person who deserves a lot of credit. Elaine, can you stand up for a second so I can pick on you? Elaine Oren, for all of her work. She was the brainchild, at least as far as I know, she was the brainchild of pulling off this incredible event. And I don't know if your committee members are here, if they would be willing to stand up. Can they stand up as well so we can recognize them? Many of the committee members who served with Elaine to pull off this seminar, are you here? They're tired. Okay. So again, thank you, and thank you, Dan Moat, for hosting us here at the National Academy. It's a wonderful thing that you did for us. Thank you to the Brill family, and thank you to all the other speakers who came before me. Now let's have some fun and enjoy the reception. Thank you.